Hello students, welcome to the lecture of hydrocarbons. In the previous lecture, we had completed alkynes and we had started the discussion of aromatic hydrocarbons. So, aromatic hydrocarbons are a different class of hydrocarbons which are very different from alkanes, alkenes and alkynes. Benzene is the simplest and most common aromatic compound which is found in various natural products and naturally obtaining hydrocarbons also. So, how the structure of benzene was discovered? It was discovered by some experimentations. So, one such experimentation was performed by Auguste Kekule in 1865. He proposed the structure of benzene that we see today. So, the structure of benzene is like this. Okay. So, if we break it up, we can write like this. A ring containing 6 carbon, all of which are sp2 hybridized and they have alternate double bonds and each carbon contains 1 hydrogen. So, this is the structure of benzene. Now, how was it deduced? Mostly it was deduced by 2 experiments. The first one we had already discussed. Benzene forms triozonide. Okay. What is ozonide? When we were studying the reaction of alkenes, we had seen that when we react alkenes with ozone, that is O3, such a structure is formed. Okay. By breaking up of one pi bond between these 2 carbons. Now, for one pi bond, one ozonide was formed. For benzene, a triozonide was observed. So, if we write this reaction, it will react with 3 molecules of ozone and something like this will be observed. Okay. So, at first this structure of benzene was not known back then, but they discovered this triozonide. So, from this was deduced that benzene must contain three carbon-carbon double bonds. Okay. This was one point. The another point was that mono-substitution of benzene produces only one product. So, if we consider a very simple alkene such as propene and we perform halogenation, then we had discussed that we get 2 kinds of products, right? So, one of them is major, one of them is minor. This was the major product, this was the minor product. So, if for one double bond, two products can be formed, then benzene has three double bonds. Why is it forming a monosubstituted product? So, this conclusion that benzene forms only one monosubstituted product led to the deduction that here for one double bond, two products are formed. Benzene has three double bonds, but one product is formed. So, this led to the conclusion that all carbon-carbon double bonds of benzene are chemically equivalent. Okay. So, all carbon-carbon double bonds of benzene are chemically equivalent. That is, they have the same chemical properties. So, different products are not formed, rather only one product is formed. And a third point was there for dye substitution. Two kind of bond lengths were discovered in dye substitution. So, let's say this is benzene and this is also benzene. Now, if these two carbons are having two bromines, here also these two carbons will have two bromines. So, how is the scenario here? In this case, it's like this. The two carbons having the bromide groups are having double bonds in between them. Okay. So, two bromine atoms here are bonded to double bonded carbons, right? But here what is the scenario? Here it's like this. The two carbons with which the bromines are bonded are having single bond between them. So, how is this possible? By observing this factor, Auguste Kekulé concluded that benzene double bonds have an oscillating nature. Oscillating nature, that is, double bonds change their positions. Okay. So, if this is the initial structure and we mark 1, 2, 3, 4, 5, 6. So, in this structure, the double bonds were between C1 and C2, C3 and C4, C5 and C6. But if the double bonds oscillate, that is the double bonds change their positions, then this double bond can come here, this can come here and this can come here. So, it will be like this. So, now the double bonds are between C2 and C3, C4 and C5, and C6 and C1. Okay. So, by all these 3 points, that is triozonide, monosubstitution of benzene produces only one product, and the different kinds of bond lengths for disubstitution concluded in this structure of benzene that we see today. Okay. So, now we know the structure of benzene. So, how many sigma and pi bonds are here? So, benzene contains 1, 2, 3, 4, 5, 6. 6 C single bond C, that is sigma. 1, 2, 3, 4, 5, 6. So, 6 CH bonds. So, a total of 12 sigma bonds and 3 pi bonds. Okay. 12 sigma bonds and 3 pi bonds. Now, this resonance of benzene, that is this oscillation of the double bonds or interchange in the positions of double bonds is called conjugation or resonance. Okay. Now, these conjugations are formed for infinite times. Okay, there are infinite possibilities because this double bond rotates and it forms like this. So, now again it can rotate. Okay. So, we get structure 1 back. So, although infinite rotations of these double bonds are possible, but we get primarily 2 structures. Okay. So, infinite resonances are possible. So, the resonances continue to happen, they do not stop, they continue to happen, and the interchange between these 2 structures go on continuously. Okay. So, these 2 are the acceptable structures. Since they are interchangeable, they are described by this double-sided arrow. Okay. So, for convenience, benzene is also described like this, that is with a 6-membered ring with a circle in between. This circle symbolizes rotating electron cloud. Okay. So, when we are talking about electron cloud, so when we were reading alkenes and alkynes, we had seen this electron cloud arises from the pi bond. Okay. So, now we have to see the structure of benzene. So, all carbon atoms in benzene are sp2 hybridized. Okay. So, if they are sp2 hybridized, then each carbon contains 3 sp2 orbitals, right, with 1 electron in each. and one p orbital, right. So, now remember the structure. If this is the structure, then one carbon can have 3 sp2 orbitals. Okay. So, with one sp2 orbital, it forms bond with another carbon. So, on both sides with 2 sp2 orbitals, the carbon forms bonds, that is sigma bonds, with 2 other carbons, and this other sigma bond is formed with one hydrogen. So, hydrogen has one S and carbon has sp2. So, this is also sigma bond. So, overall 3 sigma bonds are formed. So, 2 sigma bonds with the 2 carbons and 1 sigma bond with 1 hydrogen. Now, similarly, this carbon will also have another sp2 orbital which will be bonded with another carbon. So, ultimately, these type of bonds are formed. So, these carbon-carbon bonds are formed by, if this is C1 and C2, sp2 of C1 with sp2 of C2, and the carbon hydrogen are formed with sp2 of C1, or better to say sp2 of carbon with 1 s of hydrogen. Okay. So, like this 12 sigma bonds are formed. Now, pi bonds, that is how the double bonds are formed. So, one carbon has one p orbital, another carbon will have another p orbital. So, these p orbitals form pi bonds. So, pi is formed between p of C1 with p of C2. Now, there is no extra p orbital and valency of carbon is only 4. Here 3 is completed and one valency is left. So, one pi bond is formed. So, suppose this carbon forms one pi bond with this carbon. Now, the p orbitals of these two carbons have bonded. So, these carbons will also form pi bond between themselves. So, this is the bonding of benzene. So, we will discuss about the structure and bonding of benzene in the next lecture. Thank you.